Yeah, today we'll summarize what we learned from polynomial. I think it's 3.2, 3.3, 3.4. Now, the first question, oh, by the way, I will do some problems from the old test. I think this is from spring 19, Math 245, test 3. Now, there are problems that you can do already there, but the one I discuss here, only the one related to has strong relation to polynomial. Number 2, from that test, given a polynomial in factorized form. So once it is in factorized form, it is actually a lot easier to work on. For example, part A, let me use blue color so that you can see the difference between the problem and my solution. Find the y-intercept. So I need to find what is P0. P0 will be -2 times 2 squared times -1 times -2. It's -2 times 4 times -1 times -2. 3 negatives, that's negative. 8 times 1 times 2, 16. So the y-intercept is 0, -16. How about the x-intercept? Now, notice that it's already in factor 4, right? So the zeros are x equals to -2 with multiplicity of 2 because it's squared, right? X equals to 1, x equals to 2, both with multiplicity of 1. Now, since the zeros are all in real numbers, so that becomes x-intercept -2, 0, 1, 0, 2, 0. Now, how about the far end's behavior? The leading coefficient is -2. That's a negative number. How about the degree, by the way? The degree is 2 from here, 1 from here, another 1 from here. So the degree is 4. So basically, the leading term is -2x to the 4. Now, therefore, the graph will be bottom. That is basically if we go very far to the left, the value here will go to -infinity. When we go very far to the right, it will also go to -infinity. Okay. Now, how about the sine graph? So we have critical numbers, -2 and 1 and 2. -2, 1, and 2. Those are the zeros, right? And we also know the far end behavior are bottom. So the far right will be negative, the far left also negative. Now, -2 is a 0 with multiplicity of 2. It happens twice, such that the sign does not change. The sign on the left and the right of that 0 does not change. The multiplicity at 1 is 1. Multiplicity at 2 is also 1, such that the sign from to the left and to the right of 1 must be different. And you can see to the left and to the right of 2 also different. Okay. Now, actually, we can sketch the graph here. Let's try to sketch the graph. But I will not sketch it to scale though. Okay. So the x-intercepts are -2, 0, 1, 0, and then 2, 0. Y-intercept 0, -16. Then the graph will be from -infinity. It will touch but not cross at 2, negative 2 comma 0, and then cross here. Because at 1 it's multiplicity of 1, at x equals to 2 it's also multiplicity of 1. So that's actually the sketch of the graph. Okay. Now again, the nice thing about this is this polynomial already in factor form. The challenge, that's why we spend so much time on those theorems. The challenge is, suppose we have a polynomial not in factor form, like this question number 4. Then what should we do to find all the zeros? Part 8, use the Descartes' rule of signs to find the possible number of positive real zeros. Positive real zeros, Descartes' rule of sign, we need to see how many times the sign of the coefficient changes to find the number of variation of signs. Okay, and here you see that there are only 2 variation of signs. So there will be 2 or no positive 0. That's for the positive real zero. Now part B, use the Descartes' rule of signs to find possible number of negative zeros. To find negative zeros, the number of negative zeros, I need to reflect that with respect to the y-axis first. So I try to see how the coefficients of p negative x varies. Okay, so this will be negative 2x to the 5th plus 3x to the 4th plus 33x cubed minus 59x squared minus 51x plus 36. You see that I only change the sign if the exponent is odd. Yeah, you're supposed to plug in x equals x becomes negative x and then simplify. But you will see then if you replace x by negative x to the even power, then the sign will stay the same. Right? Now then, let's count how many times the sign changes. 1, 2, 3. So there will be 3 or 1 negative zeros. The number of negative zeros is equal to the number of variation of signs for p negative x, or that number subtracted by an even number. So it's either 3 or 1. It will not be 2 negative zeros in this case. It's either 3 or 1. Now, let's see. How about use rational zero theorem to determine the possible rational zeros of px. Okay, so px, the coefficients are all integers. So the possible rational zeros would be plus minus factors of 36, 1, 2, 3, 4, 6, 9, 12, 18, 36 over 1, 2. But you need to actually rewrite it though. So plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18, plus minus 36. Those are if I divide by 1. Now if I divide by 2, plus minus 1 half, plus minus 2 half already 1, plus minus 3 half, plus minus 9 halves. So those are the possible rational zeros. It seems like a lot. It seems like a lot, but it will actually narrow down a lot faster. Okay, so let's see what are the zeros. Part D, find the zeros using the candidates you get in part C. So let me copy that down first. That's px equals to px equals to 2x to the 5th, 3, negative 33, negative 59, plus 3x to the 4th, negative 33 x cubed minus 59 x squared plus 51 x plus 36. Of course, one of the big use of rational zero theorem is to provide us the starting points. If you need to check any number by trial and error, then you use that one. Okay, you use numbers from here first. Now, and the first number I usually use is 1. Okay, it's 1. And you can actually do it, I will do it in green for my scratch work. Okay, in your test, the one in green, you don't need to show. You do it on your scratch paper. The one in blue is the one you show. Okay, so let's say this is my scratch paper. I want to know what is P1. P1 basically, you can see, is adding all the coefficients. And if P1 equals to 0, it means 1 is a 0. So, right? Okay, this is 5 minus 92 plus 87. That's 0, right? Okay, so 1 is a 0. Okay, now, so here's the thing. Once we know that 1 is a 0, that's on my scratch paper. That's why I erased that here. Okay, then I will use synthetic division to divide by x minus 1. But Thomas, you already know 1 is a 0. What's the point of you dividing by x minus 1? Well, because once I know that 1 is a 0, then I can divide by x minus 1 and I get the other quotient. Okay, this is the part that I want to work on later on. Okay, so using the 0 that you already find, you reduce that polynomial from degree of 5 becomes later on degree of 4. And if you can find another 1 0, then you keep on doing that. Okay. Now let's start. This is 2, 4, 5, 5, negative 28, negative 28, negative 87, negative 87, negative 36, negative 36, 0. Now, is 1 another 0 of this polynomial? When I add this, it seems like that's not the case. When I add that, it seems like that's not the case. So 1 is a 0, but only multiplicity of 1. It doesn't happen twice. Now, another thing is you can take a look here. You can take a look here, P negative x. Imagine if you add the coefficients. This is 1 plus 69, that's 70, minus 100. Oh, it's not. Now, if this is 0, if you look at P negative x and the sum of the coefficient give you 0, then negative 1 is a 0. Okay, I tried to check that here and it turns out that the sum is not 0. So you can try. Let's try it here. I use green color, which means I will erase later on. When I try negative 1 to negative 1, this is 3, negative 3, negative 31. 31, this is 56, negative 56, that's negative 92. So no, it's not. Negative 1 is not a 0. Negative 1 is not a 0. Then let's guess other number. Let me try, let's say 4. 4 is in the list, right? Let me try 4. Let me use green color now because I'm not sure if 4 is a 0 or not. Let me try 4. This is 24. This is 96. This is 9. Hey, it works. Oh, surprise. Hold on. Hey, it works. Surprise. Okay, then 4 is a 0. Let me change that to blue because the green one only scratch word. So Thomas, how do you know that you should try 4? I didn't know. I just tried. I didn't know. Okay, instead of thinking hard which number you should try from here, why don't you just try it instead of wasting your time thinking, right? How about try it? If it doesn't work, that's fine. You know that it doesn't work. Okay. I did a random guess earlier. So I used 2. This is 8, 13, 52. This will be 24, 96. This is positive 9, 36, 0. Now, actually, at this point, we actually know something. Remember the Descartes' the rational zero theorem? Right now, we can update. For us to find more zeros, we can update our list right now. Okay, it will be plus minus 1, 3, 9 over 1, 2. So according to rational zero theorem, 4 will not be another 0. 6 will not be a 0. Right? You see that 4 and 6 were in our list, actually 18 and 36 and 12 also, right? Okay, but since we factor the x minus 4 out, then we can update our rational zero theorem list, our list from rational zero theorem. In fact, more things to say. Notice that there's no variation of sign here. There's no variation of sign, which means no more positive 0 from here on. Now, if you look back to part A, how many positive zeros are supposed to have? 2 or 0, right? Now, we already get those 2. We already get those 2 positive zeros. And from this quotient, polynomial quotient, we see that there's no more positive zeros. In other words, you should not try positive 2 anymore. You should not try positive, actually 2 will not work, right? You should not try positive 3, you should not try positive 9. But Thomas, 9 is in that list, that's true. Plus minus 1, plus minus 3, plus minus 9, plus minus 1/2, plus minus 3/2, plus minus 9/2. That's the list, right? But the Descartes' rule of sign says, in this case, no more positive 0. Why? These are the coefficients of the quotient, and there's no variation of sign, right? And according to our theory in part A, there should be only 2 positive zeros, and you already get those 2's. So do not try positive 3, do not try positive 9. Let's try other number. Let me try negative 3. Okay. Again, I did it by guessing. I did it purely by guessing. Okay, 2, negative 6. This would be 7, negative 21. Oh, it works. Negative 9, 0. So right now, my px can be rewritten as x minus 1, x minus 4, x plus 3 times 2x squared plus 7x plus 3. I hope you know where I get this from. 1, 4, 3. 1, 4, 3. Right? Okay. Now, Thomas, why don't you go on with that 273? You can go on if you want to. The way I see, it's already quadratic, right? So I can go on maybe by factoring. If I cannot do it by factoring, then I can do it by completing the square or quadratic formula. Okay, but this one I think is easy to factor. Plus 1 plus 3. So actually it becomes x minus 1, x minus 4, x plus 3 square, 2x plus 1. Now from there you see the zeros are, we are looking for the zeros. Okay, find the zeros and the multiplicity. Okay, so the zeros are x equals to 1, x equals to 4, x equals to negative 1/2, all of them with multiplicity of 1, x equals to negative 3 with multiplicity of 2. Now then from here, I go on, write px in factor form. This seems to be already in factor form, but it's not perfect though. It's not perfect. We have a little issue here. When it is in factor form, it has to be x plus or x minus something. So I will factor that 2 out. In fact, when it is in factor form, the leading coefficient you have here will be the leading coefficient you have there. Okay, so px equals to 2 times x plus 1/2, right? Imagine if I factor the 2 out from here. Okay, and then x minus 1, x minus 4, x plus 3 squared. List the y-intercept and x-intercept. The y-intercept will be 0.36. The x-intercepts are negative 1/2, 0, negative 3, 0, 1, 0, 4, 0. Part G, use syntactic division to find p negative 2. We will use remainder theorem. Okay, we'll use remainder theorem. So using syntactic division, negative 4, negative 1, 2, negative 31, 62. So this is 3, negative 6. This is 45, negative 90. So this will be negative 54. Okay. So for p negative 2 is negative 54. Now let's do the sine graph. Oh, what's the far end behavior? It's degree of 5, leading coefficient positive. So the far end behavior will be like this. Okay, it is bottom out. Now, can you tell what's the range then? Yeah, because the polynomial is continuous and one of them goes to negative infinity, the other's far end behavior goes to positive infinity, then the range must be all real numbers. Now sketch the graph below. You don't need to graph it to scale. So the zeros are 4, 1, negative 3 with multiplicity of 2, and then negative 1/2 with multiplicity of 1. And the y-intercept is positive 36. Actually, we know more. P negative 2 is negative 54. So at negative 2 is negative 54. Okay, so it has to, the graph should pass this guy, this guy, this guy, this guy, this guy. It must pass those. And we also know that the far end behavior is negative infinity on the far left and positive infinity on the far right. So let's put things together. This will be approximately like this. Okay, now when you sketch the graph, you don't need to graph it to scale, but you are required to actually put the number here. So not just put a dot there, you need to put the 3 also. Put the negative 1/2, put the 36, put the 1, put the 4 here. And for this guy, you may want to put negative 2, negative 54, right? And again, it doesn't have to be to scale, but it gives you a rough feeling what it looks like. Do not use graphing calculator. If you use graphing calculator, you will see that the graph will look so ugly. So ugly. In fact, one way I know somebody's using graphing calculator is by looking at the graph. Okay, because if you try to graph this, the graph looks like this. If you do it on graphing calculator, it looks like this. Very sharp, and then very sharp. So the graph is just so the graph looks so right, but then you won't be able to see the detail. Okay, you see a lot of vertical lines instead. Okay, so don't use graphing calculator because graphing calculator gives you the graph to scale, but if you once you graph it to scale, there will be a lot of things you cannot see in the given window. Okay, now that's for number 4. Let me see more. There should be more questions we can do from the test. This one here. Give me a sec. Number 5. Number 5. Oh, you know what? Let me enlarge this so that we can see it better. Let fx equals to this. Use the Carter's rule of sign to find the possible number of positive real zeros. So the same question with earlier, huh? Okay, 1, 2, oh, only 2. 2 or 0 positive zeros. 2 or 0 positive zeros. Use the Carter's rule of signs to find possible number of negative real zeros. So let's see, f negative x will be negative x to the 6 minus 4 times negative x to the 5th minus 3 negative x to the 4th plus 10 negative x cubed plus 8 negative x squared. So you will see when it has even exponent, the coefficient stays the same. If it has odd exponent, the sign will change. The sign of the coefficient will change. Then, how many times the sign changes? 1, 2. Okay, so there will be 2 or no negative zeros. Use the rational zero theorem to determine the possible rational zeros. And there's a hint there, take the common factor out first. take the common factor out first. So you see that fx has common factor x squared, right? Let me take that x squared out. So I get x to the fourth minus 3x cubed minus 4x cubed minus 3x squared plus 10x plus 8. So x equals 0 is a 0. Okay, and that's a rational number. And how about the rest? Others are c equals to plus minus 1, 2, 4, 8 over 1. Factors of 8 over factors of 1. So that's plus minus 1, plus minus 2, plus minus 4, plus minus 8. Hey, at least we get 2 zeros already for free, right? Right? So we have now fx equals to x squared, x to the fourth minus 4x cubed minus 3x squared plus 10x plus 8. Now the guessing game. Let's see for this, what's when x equals to 1, it will be 1 minus 4 minus 3 plus 10 plus 8. That's positive 12. So 1 is not a 0. Okay, 1 is not a 0. Okay, then we don't try 1. What numbers do you want to try? 1, negative 4, negative 3, 10, 8. Oh, by the way, be very careful if there's any skip. What I meant is, suppose you have negative 3x squared and suddenly just 8. Then you need to insert the placeholder there. Okay, just in case, what number should I try? Should I try 2 or 4? Let me try 4. Why not? Let me try 4. So 4, 1, this is 4, this is 0, this is 0, this is negative 3, negative 3, negative 4, negative 2. It works. No. No. I try it later. I try it later. Okay. I guess it and it happens to be right. Let me try 8. 1, this is 8, this is 4, this is 32, this is 29. This is what? 40, 232. 242. This is big number. This is very big number. Now, remember I talked about the upper bound. Let's look back to what I did last time. Remember I didn't talk about this upper bound, lower bound rules. Now I can talk about that briefly, and I will just show you under what situation we know that's an upper bound. Okay, notice that if this is a positive number, and all of this positive number, it means there's no more zeros to the right of 8. There is no more zeros to the right of 8. So on the coordinate system, let's say this is 8, right? Then there's no more x-intercept here, no x-intercepts here. Not even irrational ones. Not even irrational ones. Okay, and you can actually check the variation of signs. There's no variation of sign, right? It means to the right of this 8, there's no more zeros. Okay, 8 doesn't work. We know 4 works earlier. I will just use that 4 there. I will just use F4. I mean, I did it by guessing. It happens to be right. 1, 4, 0, 0, -3, -12, -2, 8, -8, 0. So 4 is a 0. Is 4 a 0 with multiplicity of 2? Let me try another 4. Another 4. 1, 4, 4, 16, negative, I'm sorry, positive 13. That's 52, 50. Nah, no, it's not. It's not. It's not. So 4 is not a 0 with multiplicity of 2. It is just multiplicity of 1. Actually, do you realize that I should not try 4 anymore? The 4 cannot be another 0. Why? According to the rational zero theorem. According to rational zero theorem, if you try anything, it has to be the factors of 2 over factor of 1. So your choice is only plus minus 1 and plus minus 2 right now. Those are the choices right now. You should not try 4 anymore. Duh, Thomas, you're working too hard trying that 4 earlier. Right? So you see, the rational zero theorem, Descartes' law of sign that we learned earlier, actually does not apply only for the initial polynomial. Like even in between, when we work with that, you can update your rational zero theorem and Descartes' law of sign. Okay, so if I want to go on from here, I will not try 4 anymore. I should not. Let me try 2 or -2 or 1 or -1. I think -1 actually worked, but let me try 2 first. Oh yeah, that works. Okay. Let me change it to blue color. So 2 works. Thomas, it seems like whatever you guess, you get it right. Yeah, don't you think that's actually good news? Just do something, right? Don't stare at that and expect something happen. No. Okay, nothing happened, not even in your family, if what you do is only giving opinions on what other people are supposed to do. Okay, I actually, to be honest with you, if I am your team player, the one I hate the most from my team member is like my colleagues, my team member tells me what to do. You should do this, you should do this, you should do this. I hate that. You know, the better team is the one who say, you know what, Thomas, I can do this, I can do this, I can do this, I can do this. Oh, Thomas, I cannot do that one, but let me try this. Instead of you don't try to do it on your own, but you tell other people to do it. Now, that's not teamwork. That's not teamwork. Okay, I don't want to get that kind of team member. Okay, now imagine if you do this as a team, right? Not supposed to do, but I mean, if you tell yourself, okay, what should I do? Should I try 2? And then, but I don't know if 2 works or not. Like, why don't you just try it, right? Instead of just staring at that, right? Okay, staring at the problem never solve the problem, ever. You still need to think, but in the end, it's about action. Okay, now let's go on. So this is 1, 2, 2, 4, 1, 2, 0. So at this point, our function already being factored this way. Remember that x squared from up here, right? And then we have x minus 4, x minus 2, right, from here. And then x squared plus 2x plus 1, right? Hey, but that thing is factorable. So x squared, x minus 4, x minus 2, x plus 1 squared. So the zeros are, to summarize that here, the zeros are x equals to 0 with multiplicity of 2, x equals to -1, also multiplicity of 2, x equals to 4, x equals to 2, both with multiplicity of 1. So you see, this is a polynomial with degree 6, which means it's supposed to have 6 zeros. But Thomas, we have only 4 here. No, we actually have 6. You need to count this twice because it's multiplicity of 2. 2 plus 2 plus 1 plus 1. There are 6 zeros now. Okay. Then I will go on. And what is this function in factor form? This function is equals to x squared, x minus 2, x minus 4, x plus 1 squared. How about the y-intercept? 0, 0, right? When x equals to 0, the constant part is 0. The x-intercepts are 0, 0, -1, 0, 2, 0, 4, 0. See, once you get all the zeros, it becomes easy. I should not say that once you get all the zeros. It's actually, you start from getting 1 0. Okay, you start by getting 1 zeros. Once you get 1, then you can use that. How to think of that? Imagine if you have 4 problems here. When you can solve 1 problem, then you have only 3 problems to solve, and usually the polynomial gets smaller. Okay, so please think that way. Okay, please think that way. I'm talking about not only about the math problem, but also life problem. Okay, use syntactic diffusion to divide x plus the function by x plus 3. Now syntactic diffusion will be 1, -4, -3, +10, +8, 0x plus constant 0. Don't forget those two. When you divide by x plus 3, so the number will be -3 here. 1, -3, -7, only 1, 18, -54, -44, 132, this is 140, -420, positive 1260. So the quotient is fx divided by x plus 3 is equals to x to the 5th minus 7x to the 4th plus 18x cubed minus 44x squared plus 140x minus 420 plus 1260 over x plus 3. How about the far end behavior? The leading term is x to the 6, so it's top. Means when you go very far to the right, you go to infinity, very far to the left, it also goes to infinity. Okay. Sketch the graph. 0, 0 is the x and y intercepts. What else? negative 1, comma 0, negative 1, comma 0, also X intercepts 2040, 2040. Oh, the far end behavior is top. Okay, at negative 1, it's multiplicity of 2, so it bounces. It's just touching, not crossing. At 0, it's also multiplicity of 2, it's just touching. At 2 is odd multiplicity, actually it is degree of 1, so it will cross it linearly. At 4, multiplicity of 1, it will cross it linearly. So approximately that's what the function looks like. In fact, we can say more. At x equals to negative 3, right? When x equals to negative 3, the value is 1260. Okay, so at x equals to negative 3, that's positive 1260. If you try to draw this to scale, this segment here, this part here, will look like a vertical line. Your calculator cannot put everything there. If you try to zoom that out, zoom it out, then you will just see this. That's what it looks like. Okay, so you will miss all the details necessary here. Okay, now that's for this polynomial. Of course, then we use this technique here to answer questions. Going back to our book, to answer questions, for example, let's see, 3.4. For example, we want to answer questions like maybe number, I try to look for a good one. Let's say I do number 84. .4, number 84. Section 3.4, number 84. We have this function fx equals to 2x to the 4th plus 5x cubed plus 4x squared plus 5x plus 2. And the question is find all zeros. The question is find all zeros. That's the big question. Big question. Find all zeros. My bigger question, sketch the graph. Now, I call them big questions because to answer these big questions, we need to break it up into smaller parts. For example, the first one is how many positive zeros? How many zeros on the right-hand side of y-axis? There's no variation of sign, right? We see positive, 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 right? The coefficients are all positive. So there will be no positive zeros. How about negative zeros? So let's take a look. F negative x. F negative x is 2x to the 4th minus 5x cubed plus 4x squared minus minus 5x plus 2. 1, 2, 3, 4. So there will be 4, 2, or no negative zeros. Now let's try. How about rational zero theorems? According to rational zero theorems, the zeros will be the factors of 2 over the factor of the leading coefficient 2. That's plus minus 1, plus minus 2, plus minus 1/2. But you know, together with what we know from part A, the list actually only becomes -1, -2, -1. Okay, now let's work it out. I will still use the green color for part B, find all zeros. With their multiplicity. I start synthetic division right away. 2, 5, 4, I'm sorry, -5. Yeah, that's right, 5, 4, 5, 2. Let me try -1. I don't try 1 or 2 or positive 1/2 anymore because I know there's no positive zeros, right? Okay, so I try this when x equals to -1. What's the outcome? This is -3, -3, -1, -1, 4, -4, -2. So -1 is not a zero. But wait. Hold on. What is F0? What is the Y-intercept? Y-intercept is the constant 2, right? And from here, we actually learn something new. From here, F-1 is -2. So take a look. When x equals to 0, that's positive. When x equals to -1, that's negative. Right? According to intermediate value theorem, there must be a 0 in between. Right? So what number do you have between 0 and -1? What rational number you have? -1/2. So let me try -1/2 here. Maybe work, maybe not. -1, 4, -2, 2, -1, 4. Oh, it works. Yay. So -1/2 is a 0. Now, I already tried 1 earlier. It didn't work. So actually, -1 will not work. I can try -2 though. Yeah, I can try -2. Even though you can also realize that this is 2x cubed plus. So right now we already factor it. This is x plus 1/2 times 2x cubed 4x squared plus 2x plus 4. Notice that you can do factorization by grouping already. Right? You can do factorization by grouping. But suppose you don't realize that, then okay, fine. I continue with -2. -2 I know will work. So 2, -4, 0, 0, 2, -4, 0. So my function now is equal to x plus 1/2, x plus 2, 2x squared plus which I can factor the 2 out. So the zeros are, you see this guy here, x squared plus 1 equals to 0. Solve that further. So x equals to plus minus square root of -1. That's plus minus I. So the zeros are x equals to -1/2, x equals to -2, x equals to I, x equals to -5. All of them with multiplicity of 1. So I answered that question already. Find the zeros. Okay. Now you see that one of the critical steps here is on the side of your eyes, you identify that, you know what, f0 and f-1 give you opposite sign. f0 is 2, f-1 is -2. So because polynomial must be continuous, then there must be a 0 between -1 and 0. So that's why I chose using -1/2. Okay. Now from here, then what do we see? We see what are the x-intercepts? X-intercepts are -1/2, 0, -2, 0. I and -I are not real numbers. Are not real numbers. So they don't become x-intercepts. Okay, that's one. Another thing you realize is that notice that I and -I are conjugates, right? Remember conjugate zero theorems? Okay. Then how do we sketch the graph here? If I need to sketch that, oh, what is the y-intercept? Y-intercept is 0, 2. Okay. Y-intercept is 0, 2. X-intercepts are -2, 0, -1/2, 0. Its degree of 4, I believe. Yeah, leading coefficient 2, so it's top. Looks like that. Now, it is possible, I'm not saying that it must be like this. I'm saying that it is possible the graph actually tilt around like the following. It may look like this. Maybe. Okay. That's the effect of having non-real zeros. Then you will have that kind of phenomena somewhere. It doesn't have to be here. It may be here. It goes that way. Right? Maybe. Okay. Or maybe here. Like that. You get that kind of phenomenon. But it doesn't have to. And you don't need to show that in your work also, where that tilt, that extra turning point should be. Don't worry about that. Okay. Now that's for this section, this polynomial. Now for the next 20 minutes, I will start 3.5. Oh, hold on. Not 3.5. 4.1. I cannot finish 4.1, of course. I just give you the basic idea. And then on Thursday, we do more 4.1. But here you need to memorize a lot of notation. 4.1 rational functions. Now, rational function is a rational function. I denote it by Rx. Of course, you can use Fx if you like. Okay, is defined to be a polynomial divided by a polynomial. So rational function is the quotient of two polynomials. Okay, now I will use the following notations so that we can tell this coefficients is from the polynomial on the numerator or denominator. On the numerator, I will use coefficient a and the degree n. And on the denominator, I will use coefficient b with degree m. Basically, it's polynomial over a polynomial. Let's say, for example, Rx equals to x squared minus 5x minus 6 over x squared minus 4. So you see the numerator has degree 2, the denominator also have degree 2. The leading coefficient of the numerator is 1, leading coefficient of the denominator is also equals to 1. Okay, now the first couple common questions are, the first one, the very common one, is the domain. Find the domain. And you will see the domain is all real numbers except the zeros or px. I'm sorry, the zeros of qx. Basically, you need to take out all the zeros of the denominator. You don't want the denominator to become 0. Does it make sense for you? Second, the y-intercept. What's the y-intercept? Well, basically that's R0, right? To find y-intercept, R0. So you will get a sub 0 over b sub 0. Okay, all the x terms cancels because this will all be zeros. And these all be zeros. When x equals to 0, right? Okay, that's what you get. Okay. So the y-intercept will be 0, comma a sub 0 over b sub 0. Of course, you need to make sure that b sub 0 cannot be 0. Right? Otherwise, if b sub 0, if there's no constant on the denominator, let's say you have x cubed plus 3x, then x equals to 0 should not be in the domain. Therefore, you won't have y-intercept. Okay? Now, those are the easy ones. Those are the easy ones. Let's apply that into this example 1 first. Let's apply that to this example 1. So in this example 1, part A, what's the domain? Now, for us to find the domain, we need to factor that first, though. So it relies heavily on your ability to factor. Okay, this will be x minus 6, x plus 1 over x plus 2, x minus 2. The domain will be all real numbers except 2 and negative 2. Part B was the y-intercept. R0 will be negative 6 over negative 4, which is 3 over 2. So y-intercept will be 0, 3 over 2, which you can rewrite as 0, 1.5 for the purpose of us graphing it on Thursday. Next one, how about the x-intercept? Just like before, for us to find the x-intercept, we set the function equals to 0. Actually, let me just use the one already in factor form. Well, no, I will just start from here. And how do we solve this rational equation? We multiply by the LCD, right? Now, I hope then you realize once you multiply by the LCD, then you realize one big knowledge that a fraction equals to 0 only if the numerator equals to 0. Does it make sense? A fraction equals to 0 only when the numerator equals to 0. So let's solve this. X equals to 6, x equals to negative 1. So the x-intercepts are 6, 0, negative 1, 0. But you need to make sure these zeros, these x-intercept, I'm supposed to say these zeros are in the domain. Okay, so the third principle, the third concept to find x-intercept, you will get the real zero of the numerator px, 0. Okay, but make sure that these zeros in the domain. We will have a lot of topics to talk about in these rational functions. So what I usually do is this. I will teach you part of the knowledge and example. And then later on, I will teach you more and more examples. More theory and then go back to example. More theory, go back to examples. Now let's see an example where the x-intercepts give us zeros that is not in the domain. So example 2, let our x be, let's say, x squared minus 9 over x squared plus 5x plus 6. These factors into x plus 3, x minus 3, x plus 3, x plus 2. Okay, don't do too much from there. Don't cancel that x plus 3 yet. No, not yet, not yet, not yet. Because first question is the domain. What is the domain of this function? It's all real numbers except -3 and -2. Okay, now this guy here can be simplified to be x minus 3 over x plus 2 for x not equals to -3. But it will be undefined for x equals to 3. X equals to -3. Thomas, I don't get it. I thought that they are actually equal. No, they are not exactly equal. This guy here, in our algebra 2 and algebra 1, we say that this guy is equals to this. But no, they are actually not precisely equal. They are not precisely equal. They are different. They are different. They are very small difference between those two. Okay, there are very small difference between those two. Let's do part B and part C first, and then we graph them. Okay, using my software, the Y-intercept will be 0, -9/6, which is 0, -1.5. Okay, so part C, the X-intercept, you basically solve for the numerator. You will get x equals to 3 and x equals to -3. But then you need to cancel x equals to -3 because it's not in the domain. So you have only one x-intercept, that's 3, 0. Okay, now what I will do next is I will graph both of these functions, the one I circle in yellow, and I show you the difference between those two. Let's take a look on my graphing softwares. I have y equals to x squared minus 9 all over x squared plus 5x plus 6. That's what it looks like. Let me screenshot this. Later on, I will put at my node. And the other one that I want to graph is so that we can compare that later on. X minus 3 over x plus 2. They look very similar, huh? Can you tell the difference? If you stare at the graph, you will not see the difference. There's no way you can see the difference if you look at the graph only. So do not think that, oh, Thomas, as long as I can cheat using graphing calculator, I should be fine. No, in fact, that's not true. That's so not true. Okay, let's squeeze that in a little bit. Okay, compare these two graphs here. They actually look very, very similar. They actually look very, very similar. Am I going back to my notes already? I put them back in my notes. I make them like this. They look very similar. Let's go back to the graphing. So this is the purple one is my simplified form. Now let me graph the original one. The one before I simplified. Y equals to x squared minus 9 over x squared plus 5x plus 6. Now I graph both of them at the same place. Okay, so you see they actually on the top of each other, right? But what's the difference? Let's see what's the difference. Let me change this to yellow.
It's what we were talking about earlier with the domain on one of them.
Yeah.
-3 is not included.
That's
it's
right.
an open circle, yeah.
That's right. Now, you see that they're on the top of each other, right? Do you see that now? Let me super zoom this. If you just see that briefly, you don't see the difference. But you see here, when x equals to -3, when x equals to -3, it is well defined in the simplified version, but it is a hole for the green one. You see that? Lower it even further. I play with the color so that you can see it better. Okay? I play with the color so that you can see it better. So yes, these two functions actually exactly the same except at one point. Where? At x equals to -3. That first here. Okay? These two functions, the simplified version is the same to the original one, except at x equals to -3. Now, the domain here is all real numbers except -2, right? The domain here, the domain here will be all real numbers except -2 and -3. So not only we see that the difference is like they are the same except at that one point, we also see what happened at that point. What happened at that point is it becomes a whole. At that point, it becomes a whole. Okay, so if we look back here, you will see not only that they are I said that they are different. But they are different only at one point, only at x equals to -3. Okay, so what happened is in the long run, I think I should say in long run, not in the long run. In long run, we will graph this simplified version, the r star x, I call it. We'll graph r star x because they are the same, because this function here and this r star x, they're actually the same except at one point, right? So what we will do is we graph the simplified version, then identify the whole. identify the hole. Okay, in fact, we can find what is the coordinate of the hole. We see -3. You see -3 is not in the domain of the original function, but it is in the domain of the simplified function, right? So if you want to find where is the hole, what you can do is you plug in that -3 into the simplified version. So -3 minus 3 over -3 plus 2, that's -6 over -1, that's 6. So the hole is located at -3, 6. Okay. Remember that they both have the same coordinates, right? They both have the same graph, except at that one hole. So what is the hole that you need to create that hole? We know that it happens here at x equals to -3. Okay, now we know the y. The y is at 6, confirmed by our computation. Okay. Now, furthermore, vertical asymptote, part D, going back to the theory, vertical asymptote is the equation of a line, a vertical line, x equals the zeros of q star x. Qx is the denominator of our x. That's Qx. So what is Q star x? Q star x is the denominator of the simplified version. Okay. Q star x is the denominator of, oh shoot, what am I effing doing? Hold on. I forgot to change my mode. Here. In long run, when we graph r star x, we graph r star x first. We graph this function first. And then we identify the hole. So to graph this later on, if we want to graph this rational function, we will graph the simplified version first, and then we identify the hole. That's how we will do it. Okay, now how to identify the hole? How to identify the hole? You see, -3 is undefined in the original function, but it is defined in the simplified function. So what I will do is I plug in that -3 into this one. I get the hole. Now you see, going back to that graph, if we look at this graph here, when x equals to -3, the y is 6. Right? In fact, we can see it better here. Okay, the hole is at x equals to -3, +6. Do you see that hole? Right? Now, at this graph here, x equals to -6, -3, +6, it is well defined, no hole. But we have hole here. Okay, so in future, what we will do, we'll graph this first and then do the adjustment to get that graph. Actually, yeah. And then we do adjustment to get that graph. Okay, now I think I will stop at that vertical asymptotes. I will do vertical asymptotes on Thursday. What is your suggested homework? 4.1. Oh, study for your test 3 already. Study for your test 3 already. Okay, your test 3 will be up to 3.4. Okay, now then suggested homework from this 4.1 part A. You know what? I cannot do too much here. Study from your test 3 already. Just do that one first. Okay, then, that's for today.